Oh, it's fine.
Okay, she doesn't recognize me.
No.
All of them. I know you.
Quite a few. I mean, you have to be careful of that.
Oh. Sure. You did what? Mean. It sounded so mean. You also had that like in the evening I was talking about it. Like being very nice to the same I was sitting in the phone and lunch. How did you break it? I was like, I mean, the fact that you guys. Yeah.
Yeah. It's recording. That's not a lot. Okay, with them fine.
Okay, perfect.
Don't give them bad habits.
Oh, I mean, you know, I could have done pretty right. I just wonder why.
Like you see me so small and still just look like how is that possible? And it wasn't true. I was like, shit. When was in philosophy of what's the name?
Yeah.
I was like, what is my old liberal arts tutor doing? Why should I organic in an inorganic condition? Confusion. Also the mouse yeah, because of yeah. Yeah, true. Oh. Always makes me having tutorials with a purpose. I don't know why. You know, like just that. Sorry, say it again. Oh, again.
All right.
I was like, getting very
We're going to make a start. Hello, please come inside.
It was the magic words to make people appear.
So, welcome everyone to Inorganic Chemistry 2002 for this semester. I'm glad to see so many faces. Judita and I are co-coordinating it this year, and I'm delighted that she's on board. Usually I was teaching this course on my own for the last 5 years, and she brings nice solid state chemistry dimension to the course. So, Judita.
Okay, so hello everyone. A lot of you already know me. For those of you who don't, my name is Judita. I teach a lot of the solid state that type of stuff, but here you're going to see me for lecture 3, lecture 4, and lecture 6 of the course. And I'm also coordinating your practical. So I'm the coordinator of inorganic synthesis, who I can remind you does not start until week 3. So this week and next week, there is going to be no practical. So I just came to see all of you, to say hi, and then I'm going to leave the floor to Birgit.
Maybe we can just quickly, very briefly discuss just 2 important things. The textbook, right, is Armstrong, Weller, Rourke, very good book, which you can also use for later courses, for example, main group chemistry. And there are 2 assessment points, a final exam in week 7 on everything, and weekly tutorials. You'll see there's problem sets in the manual. Those are to be done individually and turned in at the end of the tutorial on Thursday. But every week you'll have a problem set. Those need to be turned in grading. So we have a continuous assessment element and a summative assessment element, which we think is very nice. So you can keep track of the course as you go. And I don't think there's anything else to
I think you have a midterm scheduled in the timetable. Please disregard that is not going to happen. You have the weekly problem sets, so that was scheduled by default, but we're not going to use it.
Correct.
There is an upload point on Canvas for your exercises, but you're perfectly welcome to do that on paper, scan them. The only reason we have the upload point is to actually keep track of your submissions and keep your papers in one point. But just bring them to the tutorial and you're going to be
I personally, for my tutorial groups, would prefer just hard copies. Okay, I want a hard copy in my hand. But I can discuss that later with my individual tutorial groups. That depends on the tutor. Okay, so those are the assessment points, the textbook. Maybe I'll just really hit the ground running. Just some other things. Judita's 3 lectures are recorded in advance. Mine are not, so I'm going to do them live now. But someone is recording them, and she said that she would disseminate the link because we move at an extremely rapid pace in this course, very rapidly. So it's very important that you keep on top of things, and that's why I think having a recording is nice. Judita's 3 lectures are going to be slightly different. They've been pre-recorded in advance, and she's going to use the 90 minutes for a flip style session.
So for week 3, for instance, you're going to have a 45 minutes video to watch ahead of the game. So you will see me next week to come and remind you that you need to watch it in advance, and then we're going to have all this time to go through questions and additional material.
Correct. A Q&A, much like my spectroscopy course we had this morning. A Q&A followed by additional elaborations, let's call it.
One last additional question. Who of you is in spectroscopy or has already taken spectroscopy last year? Okay, that's quite a lot of people, which is going to make lecture 4 pretty interesting.
All right.
Okay, perfect. Then I will see half of you this afternoon for tutorials, and I'll leave you with Birgit for lecture 1.
Thank you, Judita.
You can come upstairs afterwards if you want to give us the file, so we can.
I can send it to you.
Because we might be a bit heavy, so if you just want to transfer it directly, we can do that.
Yeah.
Okay. Perfect. I'll make myself scarce, and I'll see you later. Bye.
Thank you, Judita. Thanks for coming. All right, so in this first lecture, this introductory lecture, we're going to look at least in the first hour, when the first half really at some old hat concepts, just to sort of renew ourselves from the core. In the second part of the lecture, we're going to look really at some fundamentally new concepts, molecular orbital theory. Now, in the actual lecture slides themselves, which I'm going to skip over, I have an introduction of myself, who I am, where I've been. I've worked in many different places, many different universities. You can look through that if you're interested just to know who's teaching you. There's some information about my research interests, sort of at the interface of transition metal and main group chemistry. That's what I've been doing. That's what I'm still doing. the research that I'm doing here in Maastricht, some representative publications over the years and stuff. So I don't want to really go into too much detail, but I'm a very active scientist, and I believe that that's very important also in education, to combine research with teaching. It's the Humboldt philosophy. So if you're interested, you can look at that. Now, let's just reflect on what the purpose of this course is. This is really an introductory course to inorganic chemistry. It's a very broad field. You have solid state inorganic chemistry, which Judith is the expert in. You have molecular inorganic chemistry. I'm the expert in that. And all sorts of other fields, right? So we're going to try and touch on as many of these as possible in not a very deep way, but in a very sort of superficial way, just so that everyone has a sort of a taste of what inorganic chemistry is, okay? And particularly, we're going to look at some main group chemistry, transition metal chemistry, and solid state chemistry. Actually, most of the main group chemistry that was originally in this course have now moved over to the main group chemistry course on to the second part of the semester. We're going to look at bonding models. We're going to look at a bit of spectroscopy. There's going to be some overlap. And this course serves as a sort of an entry requirement for more advanced inorganic chemistry courses, particularly transition metal chemistry. So today, for the first part of this lecture, I always start with outcomes. A lot of this is stuff that you already know. It's revision. We're going to revisit VSEPR theory, valence bond theory, hybridization, which is something you may or may not have done, and look at periodic trends, just very briefly, just to sort of warm up. Now, what is inorganic chemistry, right? This is my personal definition. Okay, organic chemistry is the chemistry of carbon. Inorganic chemistry is the chemistry of everything else. And in fact, these days, the fundamental chemistry of carbon itself even falls in inorganic chemistry. So inorganic chemistry is a very broad field, right? And it's kind of difficult to teach it these days because it seems to just get broader and broader all the time. You know, inorganic chemistry is sort of subdivided into these four, and there's actually more. This also seems to multiply as time goes by, but these are sort of four subdisciplines that are self-contained in inorganic chemistry. Organometallic chemistry, I'm an organometallic chemist, which is the chemistry of metals and carbon, how they bond together specifically. Those compounds are very useful in catalysis, material science, and just fundamentally important. Coordination chemistry is, well, looking at how ligands bond to metals, very important, also in drug design. Bioinorganic chemistry is the interface of biology and inorganic chemistry, a beautiful field, something I've also been involved in. And then solid state chemistry. Now, we're going to actually look at organometallic chemistry, coordination chemistry, and some solid state chemistry in this course, not so much bioinorganic chemistry. And we're going to look at this sort of in a survey style fashion. So it's like a survey course. Okay. Now, the beauty of inorganic chemistry is because you're using metals, you have this beautiful structural diversity. And with the problem, not the problem, but the limitation with organic compounds is you just have a limited number of orbitals. With transition metals, in particular, because you've got d orbitals, you can make all sorts of weird and wonderful bonds, okay? But what we have here are kind of the organic molecules, alkynes, alkenes, and alkanes on the left. And you can see it's possible to make sort of analogs of those containing metals. You'll see in the middle here, you have a tungsten-tungsten double bond that's somehow akin to an alkene, but not really. You can also make triple bonds. Here's an osmium-osmium threefold bond, much like an alkyne, but that's between two metals. And you also have, so those would be considered formally inorganic compounds, and you have organometallic compounds where you have this combination of a metal and a carbon atom. Again, you can see you have a metal-carbon triple bond, a metal-carbon double bond, a metal-carbon single bond. Again, kind of in a close analogy to an alkane. Those are called, incidentally, on the right there, that would be called a transition metal alkyl compound. That's a carbene, and that's a carbine. And then, time permitting, we're going to get our teeth stuck into some of these later in the course. But you can see that it's possible to actually make things that are akin to what we already know from organic chemistry, kinda. And you can even make more exotic things because of these d orbitals, like you can make 4- and 5-fold bonds. Now, this is quite weird, right? Imagine a molecule that has 2 atoms bearing a 4-fold bond, so 8 shared electrons. This thing on the left was made in 1964, 1965 by F. Albert Cotton. It's the first example of a so-called quadruple bond. He isolated it. And this over here was made by Phil Power at the University of California only in 2005. That's relatively recently. And it was the first example of a molecule featuring a quintuple bond. Now, the reason why you can have this, you certainly can't have this with carbon. You can have it with metals is because you have these d orbitals, right? And those can participate in bonding, and then you get beautiful structural diversity and interesting bonding modes between metals that you do not have with the lighter elements. And here are some examples just showing the beautiful structural diversity in inorganic chemistry, because it's kind of, you know, taking advantage of these d orbitals, but also you have electron deficient compounds like that one over there. Diboranes are electron deficient, so you have these interesting 3-centered 2-electron bonding modes like there as well. That's, by the way, a very reactive compound, trimethyl aluminium. It burns on contact with air. You have these interesting bridged hydride species, lithium compounds, and these down here, right at the bottom, are called clusters, right? They're inorganic clusters. We learn about them in detail in the 3000 course. And then we have some beautiful organometallic compounds here called sandwich compounds. Beautiful structural diversity and non-classical bonding. Okay, if you look at these guys here, you have sort of these aromatic rings sitting like a hat on the metal. How's that possible? Well, it's possible because you've got a metal. It's got d orbitals. Right, it's not that simple, but that's really the reason. And of course, you have all sorts of interesting and expected geometries, right? We can work with sort of carborane type systems, boranes. So there's a lot of structural diversity in inorganic chemistry, which covers both the main group elements and the transition elements. Now, in the late 80s, actually, the American Chemical Society, I think they still do this actually, selected a molecule of the year, okay? And it's interesting to note that from 1989 to 1992, 3 out of the 5 molecules that they selected were inorganic molecules, okay? So this is an important field. DNA was the molecule of the year in 1989. Actually, 4 out of 5 were inorganic. Only 1 was organic. That's a biomolecule, obviously. But, you know, diamond, well, actually, this is 4 years, sorry. So 1 out of 4 was organic. 3 out of 4 were inorganic. This is the structure of diamond. That was the molecule of the year in 1990. This is buckyball Buckminster fullerene, an allotrope of carbon. And this is NO. It's a radical, and actually a very important ligand in biology and also in inorganic chemistry in general. So it's an important field. It's very broad. There's many subdisciplines. It's a very active field in terms of research. And you have enormous structural diversity and many unanswered fundamental questions to this day, particularly fundamental questions concerning the fundamental nature of bonding between atoms, right? There's many unanswered questions, and there's many scientists working on trying to understand how atoms bond together fundamentally. And many of those questions are unanswered, particularly relating to multiple bonds between heavy atoms, because it's very different from carbon. So that's kind of a very intuitive and personal introduction to the field. I'd like us now to sort of revise some of the stuff that you should have done in the core. And of course, the starting point is the periodic table. We've all seen this. We can divide it into the various groups, the alkali metals, the alkali earth metals, transition metals, metalloids, non-metals, halogens, noble gases, lanthanides, and actinides. Now, inorganic chemistry concerns, as I said, basically everything except organic compounds. But even in some cases, those can be included in our definition of inorganic chemistry. Now, we know from the electron configuration of these elements right? So we talk about the S block, the P block, the D block, the F block, and that comes from what the outermost valence shell is, what the outermost electrons are populating. So the first two groups are called the S block. The transition metal are called the D block because, of course, the valence electrons are sitting in d orbitals. That's what they look like. Then we talk of the P block and, of course, the F block elements down here with these beautiful F orbitals. So you can talk about the periodic table as in terms of groups, and you can talk about it in terms of blocks. Okay. Now, that's what I just said. Now, what I'd like to review now are the periodic trends, which are very important sort of always to have in the background. And there are really four important ones: atomic radius, atomic size, ionization energy, electron affinity, and electronegativity. And many of these can be understood in terms of shielding, because you're going to have the nucleus, which is positively charged, a cloud of electrons around, of 4 electrons and valence electron. Somehow the interplay between those two things are going to, for example, if you have high shielding from the core electrons, then it's going to have consequences for the size of the atom, but also for the ionization energy, the electronegativity, and electron affinity. So shielding is important. Electrons shield positive nuclear charge. Now, this is a very nice picture looking sort of at scale of the atomic sizes of atoms across the periodic table. Now, what trend is immediately apparent? Yes, what's the trend?
Down to the left increases its size.
Correct. Or it increases as we go down a group and decreases as we go across the period Y. This is something you should know. 3 o'clock in the morning, if I wake you up, what's the reason?
Number of protons and neutrons.
Correct. Well, not number of neutrons, number of protons. As we go down, we're adding another shell, right? And that gets further and further away from the nucleus. That gets bigger. But within a period, as I go across, I'm not adding another energy level. I'm just populating an existing energy level with extra electrons. But every time I go across, I'm adding 1 extra proton to the nucleus, which means it increases the positive charge. And so the thing gets smaller, right? Because there's an attraction between the outermost electrons and the nucleus. So on average, you see a decrease as you go from left to right and an increase as you go from top to bottom because of the increase of the positive charge of the nucleus. And you can see that very nicely expressed here. This is a plot of the atomic radius in angstrom, 10 to the minus 10 meters, as a function of atomic number. And you can see every time we go to a new period, we go up in the atomic radius. So from lithium to sodium to potassium, we're increasing because we're adding that extra shell. But as we go across the period, say from lithium to neon, or from sodium to argon, or potassium to krypton, and so on, it decreases for the reason I just mentioned. Because we're not adding another energy shell, we're taking the existing shell, we're just putting it in an electron each time as we go across and adding a proton, and that results in a contraction because of increased nuclear charge. And that's a very clear trend. Now, an interesting phenomenon is so-called F block, or actually more correctly, lanthanide contraction. Now, if you look at if you look closely, this diagram doesn't really do it justice. But if you look at the lanthanides, you have a phenomenon called lanthanide contraction. As you go from left to right of the lanthanides, from lanthanum all the way through to ytterbium, the atoms get smaller much faster than would be expected. And the reason for that is the ineffective shielding offered by the F orbitals. So F orbitals don't offer very good shielding from the positive nucleus. And so with lanthanides, you have this contraction effect because of the F orbitals, which don't shield as well as other orbitals. So shielding plays a role. Now, that's one trend, atomic size. You can, by the way, talk about different types of atomic size. You can talk about the covalent radius. You can talk about the ionic radius. So I don't discuss that. We were just looking sort of at the atomic radii. You get different types of quantifications of that. The ionization energy, what is ionization energy? Someone tell me.
Energy required to remove one electron from the atom shell.
Correct. It's the energy required to remove an electron from a neutral atom in the gas phase. Okay. And that would be the first ionization energy. You can have a second and a third and an nth ionization energy. Okay, but let's look at the first ionization energy. The energy required to remove one electron from a neutral atom in the gas phase. And what's the trend? This is a plot of ionization energy to atomic number. So we go from helium to radon, it goes down. Right, so we go from lithium to francium, it goes down. What does that mean? It means that
it's easier to take away an electron?
Correct. We require less energy. And that makes sense if we go back to our diagram of atomic sizes. Because obviously, if I take cesium and I compare it to lithium, see that outermost electron, right, in the outermost S shell is much further away from the nucleus, which is tugging on it, than in the case of lithium, and so it's easier to remove it. So the first ionization energy of cesium will be much, much lower than that of lithium. Okay, but again, as I go across the period, for the same reasons as with atomic number, because I'm increasing the nuclear charge, that outermost electron gets closer to the nucleus and it requires more energy to remove it. So atomic size and first ionization energy are kind of intimately interrelated with each other. Okay, and here you have the two trends. You can see they kind of mirror each other in a way, right? You can see there we go from helium to radon, there we go from helium to radon. It's very similar arguments. Electron affinity is defined as the energy required to detach an electron from a singly charged negative ion. Okay, what we're doing now is we're not taking a neutral atom and removing an electron in the gas phase, like first ionization energy. We take a charged atom and we take the electron out so it's kind of the inverse process, if you will. And if we look at electron affinity, you'll see that the electron affinity here also depends on, there is a periodic trend here. You can see as you go from fluorine to iodine, there is a sort of a decrease in the electron affinity here measured in kilojoules per mole. But electron affinity is not as obvious as the others. Electronegativity, sort of, this is the fourth one, is really, my personal definition is what is the desire an atom has, a neutral atom, to have an extra electron? And that desire is driven by whether or not it's got a complete or incomplete shell, one of the reasons. Now, you get different scales of electronegativity. There's nothing absolute. Here are some scales. The Pelling scale is the most common. Actually, there it's measured according to bond dissociation energies, right? And there's actually an example. So if you know the bond dissociation energies, you can actually use that to sort of write down the electronegativity of a specific atom or element. But there are other scales as well. For example, the Mulliken scale is the average, that's a typo there, of the first ionization energy and electron affinity. So again, it tells us that all of these trends are somehow interrelated with each other. And electronegativity is kind of, you can think of it as a combination of ionization energy and electron affinity, which kind of makes sense based on the definition I just gave, right? Now, if we look at the, and there were many other scales as well, Sanderson, Allen, and so on, just so that you know, all with formal definitions. This diagram over here, I think, very nicely shows the trend in the electronegativity associated with the elements. What's the trend? It's very clear. What's happening there? So the relative height of these bars reflects the relative electronegativity, and the electronegativity values are listed here according to the Pauling scale. So which element is the most electronegative? Fluorine. Why? I mean, intuitively. It's the smallest what?
Something about like, the smallest atom that they were from where.
Yes, it's the smallest halogen. We just thought it's got a very small size. Remember that whole atomic size trend. But what else about fluorine? It's a halogen. And if you look at the electron configuration of a fluorine atom, it requires just one electron to do what? Complete its shell. So it's going to be highly electronegative because it's desperate for that electron to complete its shell. And if it gets that electron, it's happy. It's got its octet. All the halogens are electronegative, right? Pretty electronegative. But there's a decrease in electronegativity because, you know, you have this increased distance going down the period. So the electronegativity drops off. But you can see this beautiful trend going from boron to fluorine, the stepwise increase in the electronegativity as predicted from the other trends. So electronegativity is super important because difference in electronegativity between bonded atoms actually is going to really have a direct effect on bond polarity and other things, bond association energy, and things like that. So overall, these are kind of the trends, okay, right? Kind of as we said, all of the trends, electronegativity, electron affinity, and ionization energy sort of increase bottom left to top right, with atomic size actually being the one that stands out as being in the opposite way around. So those that's a quick summary of the four main, let's say, characteristics associated with transition metals. I now want to just very briefly review the Schrödinger equation and some basics associated with atoms. This is not important. Remember, the solution to the Schrödinger equation gives us indirectly the wave functions. The square of those wave functions then gives us probability density plots, which then translate into molecular orbitals, atomic orbitals, right? That's the process. And we learned in the first year course that, of course, you know, we have different types of orbitals with different shapes. You need to really know this, especially the d orbitals in this course, all of them very well. And also the F sometimes if you're an F block chemist. But we learned that you have four quantum numbers, remember, that characterize each of these orbitals. Remember, and these orbitals are regions in space that are probabilistic regions in space where electrons can be found. So this is a probability in quantum mechanics. Right? The solution to the Schrödinger equation, again, gives us a wave function in principle. We plot the square modulus of that function, of that wave function, as a function of distance from the nucleus. We get a scatter plot, and that's the orbital. Right? We draw these as boundary surfaces. So this looks very nice. Remember, this is not a closed surface, it's a distribution, but we draw it like this for simplicity. We learned that four quantum numbers that characterize these orbitals, NL, M subscript L, and M subscript X, okay? And each of them tell us something about the orbital and where it is in the atom, which energy shell, which subshell type, which orientation in space. The last quantum number tells us whether it's spin up or spin down. Pauli's exclusion principle, remember, tells us that no two electrons can have the same four sets of quantum numbers. So actually, these quantum numbers are like an address, you know, for sending a postcard somewhere. It tells you where in the atom that electron is sitting. And an orbital can only have two electrons one spin up and one spin down. Okay, so we have Pauli's exclusion principle and Hund's rule. What's Hund's rule?
That spin goal over those electrons need to occupy orbitals alone before they're paired up.
Correct. The rule of maximum spin multiplicity. For example, if you put 3 degenerate p orbitals and you want to put 3 electrons in them, each p orbital is going to get 1, rather than putting 2 in the first and then an unpaired in the second. Same with p orbitals. So Pauli's exclusion principle and Hund's rule, the rule of maximum spin multiplicity, are very important. And of course, this again, just for the sake of brevity, is a description of what these 4 quantum numbers are: principal quantum number, distance from nucleus, energy level, angular momentum, subshell type. Magnetic is the orientation and space of the subshell type, and the spin is, well, spin plus and minus a half. You know, you probably, I hopefully learned about the Stern-Gerlach experiment and all that stuff. So this is really by way of revision. Now, what you also did in the core is VSEPR theory. And what does VSEPR stand for? Valence shell electron pair repulsion, right? You should know this. It's a very simplistic model that has some utility in predicting the shape of main group element compounds. It doesn't work with transition metals. It completely breaks down if you try to, for example, use it to predict the shape of, I don't know, a gold molecule or something like that. But it works reasonably well with main group elements. Now, the take-home message, again, this is revision, when we're drawing a Lewis structure and using that to invoke the molecular shape of something, is to position bonding and electron pairs as far away from each other in space. And remember, the other thing we're doing with VSEPR is we're looking at the relative repulsions between bonding and lone pairs to actually predict the molecular geometry based on the Lewis structure. So recall, lone pair repulsion is greater than lone pair bonding pair repulsion, greater than bonding pair repulsion. Now, if you cannot draw a Lewis structure, you can't predict the geometry correctly, as I'm sure you remember from the core. So getting the right Lewis structure is key in this game. And here, just to remind you, we have sort of the full picture of VSEPR theory. Remember, you're looking at really the relationship of groups, or let's say the types of groups around the central atom, how many electron pairs there are, if they're bonding pairs or lone pairs within each sort of family. So if you've got 3 groups around, or 3 electron pairs around a central atom, the electron pair geometry is trigonal or trigonal planar. And if you start replacing those with lone pairs, you're going to get deviations in the molecular geometry. Same goes for if you've got a 4-coordinate system, you can start replacing those sequentially with lone pairs, and it goes from tetrahedral to trigonal, pyramidal, or bent, water being an example, and so on. Trigonal, bipyramidal, replace one of these groups with a lone pair, you get seesaw. Do 2, you get T-shape. Do 3, you get linear, and so on. Beautiful, a beautiful simplistic model. Now, and you can do the same thing for octahedral. You have these deviations in the molecular geometry depending on the number of lone pairs you have. Now, the nice thing about VSEPR theory is that we have these repulsions. We have these repulsions, and lone pair repulsions are much larger than lone pair bonding pair repulsions, which are larger than bonding pair repulsions. And so the theory for simple molecules accurately predicts, if we have this series of related molecules, methane, ammonia, and water, sorry, those 2 lone pairs should be sitting on the oxygen there, okay? These all belong to the family of tetrahedral molecules, but you have replaced one of the groups in ammonia with the lone pair, so that's trigonal pyramidal molecular geometry, and this is bent molecular geometry, okay? And what do you notice for the bond angles? What happens? they increase. And these are actual measured bond angles from crystallography. So 109.5, 107.8, and 104.5, okay? Now, that bond angle has gotten smaller. Why? As we go from left to right.
From the lone pairs.
Correct, correct. So here I've got one lone pair. So that cloud is going to be pushing on that one and force those bonds in. So we're going to have a roughly 2 degrees decrease in that bond angle. And if I replace yet another atom with a lone pair, the repulsion is going to be even greater. And I lose roughly 3 degrees in the bond angle. Okay. So this is something that is very nicely predicted, let's say in simple test cases for VSEPR theory. But unfortunately, and here's some practice examples that you can try out at home. These are hypervalent ones. Remember, they extended octet. The problem is that VSEPR theory doesn't always work. And in fact, it breaks down, well, most of the time, as far as I'm concerned. We have more sophisticated theories to deal with it. In particular, if you look at the actual geometry of heavy elements like tin and germanium and lead and so on, and you use VSEPR theory to draw those, it breaks down. It doesn't work anymore because the lone pair repulsions no longer work as with heavy or with lighter elements because of something called the inert pair effect, okay? So if you have a stereochemically inactive lone pair, then actually, you know, you don't unfortunately have, you don't predict the geometry correctly anymore. So it works for light elements, but when you start having lone pairs in heavy p-block elements that are stereochemically inactive due to the inert pair effect, the model no longer works and it doesn't correctly predict geometry anymore. Okay, and for that we have molecular orbital theory. But nevertheless, it's a good starting point, and it's something that, you know, is good enough for, let's say, an intro course. But, you know, we need to move towards something more sophisticated. The other problem with VSEPR, of course, is also doesn't take steric repulsion into consideration at all. It just looks at the electron pairs around the central atom, not the size of the substituents. And you're going to have situations where, because the substituents are very large, you know, you have all sorts of deviations from what's predicted from that nice, neat little table that I showed you, right? So that's just, you know, that's kind of Mickey Mouse stuff. So here we have to move in a direction of looking at things in a more sophisticated way. Now, valence bond theory is intimately, I would say, intimately connected with VSEPR theory. They're different, but they're kind of related. So if I draw a Lewis structure or something, and I want to kind of have some sort of idea of which orbitals are actually overlapping with which to explain the bonding, I can use valence bond theory, which was one of the first theories to try and formally explain atomic overlap or atomic orbital overlap within a molecule, okay? And it sort of does have some sorts of quantum mechanical elements in it, so it's not such a Mickey Mouse theory. It's quite rigorous and robust, but it also breaks down, unfortunately. But nevertheless, we have to go through it. It's a good approximation and it invokes hybridization. Who's done hybridization here? Okay, that's troubling. Okay, so what we're doing with valence bond theory is we're looking at the localized picture. We kind of looking at, okay, we've got this molecule, ammonia. There's a nitrogen atom, 3 hydrogen atoms. What's happening there? What orbitals enable that bonding to take place? And what is the overlap between which orbitals that are situated on the hydrogen and the nitrogen and nitrogen atom? What is that overlap? Is it an overlap between an S and a p orbital? Or, you know, so it's trying to look at what's happening between atoms in a localized fashion. So it's a localized, simplistic way of trying to rationalize bonding. And in valence bond theory, by the way, also in molecular orbital theory, which we're going to unpack in a moment, we get different types of bonds. Okay, we get sigma bonds, which are bonds that are symmetric about the internuclear axis, expressed differently, they're head-on bonds. We've got pi bonds, which have a nodal plane in the internuclear axis. And a simpler way of thinking about that is they side-on bonds. Right? This is a sigma bond. This is a pi bond. And we have something else which is quite rare, and that's called a delta bond. This is a delta bond where their orbitals overlap like this. Sigma bonds are much stronger and more stable than pi bonds, which are more stable than delta bonds because of the overlap, the degree of overlap between the orbitals. So in valence bond theory, we're looking at orbital overlap in a localized between two atoms. It's a localized picture. And here we just have some examples. You know, these are sigma type overlaps. You call this as an SS overlap. You have an SP overlap or a PP overlap. Notice the sign of the wave function in the lobes of these orbitals. It's always plus and minus. Don't forget that. Right? We get that from quantum mechanics, from the fact that it's a wave. Going to become important in a moment. Here we've got pi type overlaps. Notice here we've got a pi type overlap between two p orbitals. You can also have a pi type overlap between a p and a d orbital. Actually, that's perfectly okay. And you can also have pi type overlaps between two d orbitals. We saw those examples in the beginning of the lecture where I said we have d orbitals which can be used for multiple bonding. There you can actually see an example of how that operates. But those are pi symmetric. These are sigma symmetric. And as I said, you then have quite rarely, but it becomes important if you want to make a 4 or a 5-fold bond between two metals, a delta bond, which is, I bet, something most of you haven't heard of. How many have heard of a delta bond? Okay, well, okay, so this is an interesting character. Now, that's the one side of the picture as we look at, so that's the type of bonds we have by valence bond theory. Sigma, pi, and delta, but we also have now this notion of hybridization. Now we need hybridization in valence bond theory for the following reason. Let me give you an example of why we have hybridization. Let's take, this is something everyone should have done, but apparently you haven't. Okay, so here's methane. We know from VSEPR theory that it's tetrahedral, right? We can draw the Lewis structure. I mean, this is like something you can do at 4 a.m. after a night of partying in your sleep, hopefully, right? There's the Lewis structure. Now, if we look, if I want to use valence bond theory to understand which orbitals are overlapping between this carbon atom and these hydrogens, a good place to start is looking at the electron configuration of a ground state carbon atom. Right, this is carbon, the electron configuration. Does everyone agree? Right, carbon has how many electrons? It's got an atomic number of 6. 2, 4, 5, 6 up applied once it's a ground state. Electron configuration. Now, if I look at that, how many unpaired electrons do I have? 2. Now, if I want to make bonds with hydrogen atoms, typically they need unpaired electrons, don't they? And the way this thing is sort of looking, at least in its ground state, if I have hydrogen atoms which has one unpaired electron in the S, how many bonds will I be able to make the way things stand now? 2. But how many do I need? 4. So the trick is to say, okay, why don't we mix the S and the P, hybridize them, mix, hybridize, and then what you're going to get is you're going to get 4 equivalent sp3 orbitals. And those 4 electrons are then going to go and sit in each of the equivalent sp3 hybrid orbitals. And now we can make the methane. So in fact, the way to think about methane is that you have 4 hybridized, looks something like this. This would be the valence bond picture. You've got the hydrogens, and you've got each of these as an sp3 hybridized orbital. The sp3 hybridized orbitals energetically lie between the s and the p because we've mixed them. So each of these is an sp3 hybrid orbital. And so you characterize this overlap as a sigma s sp3 overlap. That would be the valence bond picture for methane. Okay? So we need to invoke sometimes, not always, but sometimes we need to use hybridization to actually figure out what's going on. And this is the example for ammonia, which is very, very much related to what we just saw for methane. Notice that's the ground state of nitrogen. Now, one could say, okay, well, let's just leave it. Now, here's an interesting thing. Why do I hybridize it? Because if I look at the ground state, nitrogen has three unpaired electrons. The formula of nitrogen, of ammonia, is NH3. So why don't I just take that guy as is and just take 3 hydrogens with 1 s electron and just link and just hang them onto each of these p orbitals? Done. Why do I hybridize it?
Because of the geometry.
Right, explain.
So the p orbitals will not be oriented in a way which would agree with
Absolutely. These 3 p orbitals, what is their relative angle between each other? They're orthogonal to each other, 90 degrees. The bond angle in ammonia is, however, what? 107.2. So that's a very big difference. And therefore you have to invoke hybridization if you're using valence bond theory to get that bond angle right. That's why we do it. So again, I'll hybridize it. I mix the 2s orbital with the 3 2p orbitals, and I generate 4 equivalent sp3 hybrid orbitals. And then I take all the electrons, which in this case is a total of 5, put them in there. One of them is going to be a lone pair. That's the sp3 hybrid orbital with the lone pair. I have the 3 remaining hybridized orbitals, each with 1 electron inside, and then I hang a hydrogen on each of those. So this would again be a sigma sp3s overlap, valence bond picture of ammonia. Now, we can play that game across the board. This is very useful in predicting what hybridization you expect, depending on how many atoms or groups are around the same atom in valence bond theory or hybridization. They're kind of interlinked. So if it's linear, it'll be sp. If it's trigonal, planar sp2. If it's tetrahedral, sp3, as we've just seen. Then you have dsp3 and d2sp3. Now a note on this. What I'm saying here is actually rubbish, right? It's wrong. It's just wrong. It's a model. It's a model, but it's not correct. But I'm not going to change that, because this is sort of the traditional way of teaching it. It turns out, for main group element compounds, not to belabor the point, but I have to tell you this for the sake of my own conscience, that in main group element compounds, d orbitals do not participate in bonding. That's something that was shown about 20 to 25 years ago, right? Now, this stuff has been taught for the last 40 years. And if you look at any chemistry textbook, including Silverberg, this is what's going to stand in there. It's not correct, though. It's not correct, because d orbitals don't participate in bonding. However, one can have a sort of an argument about whether it's good or not to teach this to students. My argument is, for historical reasons, it's fine, even though it's subsequently been shown that d orbitals do not participate in bonding of main group elements, because it's a model. It's a model. It's a simple model. And if we invoke d orbital bond participation, that's how we can get hypervalence. That's how we can get d2sp3 hybridization. Okay, but if we mix d orbitals in with the sp3, then I'm saying that they're involved in the bonding, which is not really correct. So just remember that, but let's run with it. If I want to look at the valence bond picture of something like phosphorus pentafluoride, I have to hybridize it. And this time the phosphorus atom, because it's trigonal bipyramidal, will undergo a dsp3 hybridization, and that's what that looks like. Okay, so what I'm doing there is I'm taking one d orbital, right? One d orbital, there's 5 available, but they're empty. I'm taking an s and 3 p orbitals and I'm mixing them up, right? And so what I actually see here, what you see here, okay, I've just drawn them already hybridized. P star means it's being hybridized. 5 equivalent dsp3 orbitals. So if you write down the electron configuration of phosphorus, right, and then you take 1p, what am I saying, 1d, 3p, and 1s orbital, and mix them up, hybridize them, you're going to get 5 equivalent dsp3 hybrid orbitals, put an electron in each of those, and fluorine then has 1 unpaired electron. You can just hang it on each of those orbitals. So you end up, in fact, from the valence bond picture, if you allow d orbital bond participation, which is very naughty, but let's do it, with a sigma, this would be a sigma p dsp3 overlap. But that's how this works. And of course, you can play the game further. And here we have sulfur hexafluoride, where you have now actually, and this is actually very nice because here I've got the ground state sulfur atom, right? That's its electron configuration. And I now just pick up one of those d orbitals because they're hanging around, they're empty and close by. That's how the theory goes. Mix them all up. Now you get a d2sp3 hybridized orbital with 6 electrons in it. Okay, so S star is the hybridized version, and then you hang a fluorine on each of those. You get those orbitals to be closed, and Bob's your uncle. That's how this works. Valence bond theory is looking at localized bonding and using a hybridization very often. The orbital bond participation. When I was teaching this in Germany, was absolutely, in Germany, they're very strict about this, but they've changed everything. They said, well, this is wrong, we can't teach students this. But in other parts of the world, people still teach, and I've checked this very carefully, the orbital bond participation for valence bond theory to explain hypervalence and to explain the extended octet. They say, well, we'll throw in some d orbitals. It's not correct though. And there is a way of teaching this without any d orbitals. Right? And that's how I used to teach it in Germany. But I secretly always said, you know, I don't really want to do that because it is also for historical reasons that we invoke the orbital bond participation. Now, just the question, when you did this in the core, how it was done in this way, I imagine, correct? Right. So the truth is, it's not really correct. And that's just the fact. Because very clever people in Germany actually calculated with quantum chemical calculations to see if d orbitals actually do participate. And the answer was no, not at all, not at all. So there's all sorts of other ways that you can think about this bonding. And if you're interested, you can come to me at the end and I'll show you how you can draw a Lewis structure of something that's hypervalent without using d orbitals. It doesn't violate the octet. Okay. But I don't want to open a can of worms. For the purposes of this course, let's stick to the orbital bond participation. But if you feel strongly compelled not to, that's fine too. So valence bond theory is a localized bonding picture. Okay, we're looking at types of overlaps between orbitals. Just for the sake of completeness, you know, you should think about something like ethylene, right, where you've got a combination of an sp2 overlap between its 2 carbon atoms, a sigma bond and a pi bond. So look at that. That's the valence bond picture. What I want us to look at now, very important, is molecular orbital theory. Now, this is divorced from valence bond theory, because this is per definition a non-localized bonding picture, bonding model. And molecular orbital theory is, as far as chemistry bonding models goes, the queen of all bonding. Right? You have all these other models, valence bond theory, BFEPR, crystal field theory, which we're going to discuss next week, and they're all pale in comparison in terms of predictive power and correctness with molecular orbital theory. here are some outcomes of what I want us to discuss. I want us to look at the ideas, the fundamental ideas between MO theory, just be able to construct simple MO diagrams, understand what SOMO, HOMO, and LUMO means. That has something to do with frontier so-called orbitals, and using this to predict patterns and reactivity and properties of simple dinuclear compounds. We're not going to go further than dinuclear, homo and hetero, dinuclear systems. In the 3000 course, we really go wild with molecular orbital theory. We're giving it restricted to just 2 atoms. Okay. And then ultimately be able to actually draw molecular orbital diagrams yourselves. So what we know is that, as I said at the beginning, and we all know this, that atomic orbitals are essentially waves, right? We get that from the wave equation. And waves, per definition, as we know from basic intuition, waves have positive and negative, has a crest and a trough, essentially. And so in 2 waves, in a pond, or any waves, 2 waves of light interfere with each other, you're going to have positive or constructive and destructive interference, right? You're going to end up with crests and troughs. And molecular orbital theory is saying, okay, let's take that into consideration, right? An atomic orbital is per definition derived on a wave function. So if 2 atomic orbitals overlap with each other, I'm going to have a constructive and a destructive interference, which corresponds to a bonding and an anti-bonding interference. A constructive and a destructive interference, like with waves. Now, if I want to build up a molecular orbital diagram, this is now a non-localized bonding picture that's delocalized over, in principle, the whole molecule, right? It's not localized anymore like we had with valence bond theory. And we talk about the linear combination of atomic orbitals. What we're doing there is we're saying, okay, I want to build up a molecular orbital, and the atomic orbitals from the individual atoms I'm going to kind of mix together in a certain ratio, right, to generate a molecular orbital. Now, and the purposes of this class, we're just looking at diatomics. So what we're looking at is generating a molecular orbital, right? That's the description of a molecular orbital. And Ca and Cb are weighting coefficients. Weighting coefficients, how much I'm going to put into the mix. And this guy over here will be the atomic orbital from atom A. This will be the atomic orbital from atom B. And I have the plus and the minus because I've got this constructive and destructive interference. So that's going to generate, in fact, 2 sets of molecular orbitals. One will be bonding, one will be anti-bonding. And for every bonding orbital, you always have an anti-bonding orbital. The anti-bonding orbital, remember, is is a destructive interference, and bonding is constructive bonding. Okay, and that's what I just basically said here a moment ago. Now, let's look at hydrogen. Let's look at hydrogen, the simplest molecule, H2. Now, what do we have in hydrogen? If I bring 2 hydrogen atoms together, what does each hydrogen atom have? An S orbital. So if I take that, if I want to build up a molecular orbital picture of hydrogen, how many orbitals am I going to have? How many molecular orbitals? 2. I'm going to have, let's look at it pictorially. I'm going to have a bonding and an anti-bonding orbital, quite simply. So what I'm doing here is I have here my 2 hydrogen atoms, right? There's only 1 orbital involved in this, so I'm going to have 2 orbitals in, 2 atomic orbitals in from atom A and atom B is going to form a sigma and sigma star orbital. Now sigma means bonding, sigma bonding, and sigma star means anti-bonding. So I'm going to form a bonding and an anti-bonding orbital. And this is then the molecular orbital picture of hydrogen. Now, what you see here, these are the 2 orbitals. This is actually the mathematical formulation of it. 1 over root 2 the atomic orbital coming from the 1s orbital of A and the 1s of B, notice there's the plus, there's the minus. Remember, because plus is constructive bonding, minus is destructive anti-bonding. The 1 over root 2 is a sort of a coefficient that tells you how much of each atomic orbital you're going to put in there. That's also sometimes called a normalization coefficient. Okay, so don't worry too much about that, but it tells us just that I'm putting the same amount from atom A and atom B to make this. And this is what the orbital actually is going to look like. Notice that it's delocalized over the whole molecule because that's the molecule. Those two dots there represent the two nuclei of the two hydrogen atoms. This is what the sigma orbital is going to look like. This is what the sigma star orbital looks like. Notice that you've got different phases because what I'm effectively doing is I'm taking a plus and a minus S and I'm putting them together, and that causes a destructive interference. And that's why I end up with that over there. Now, each hydrogen atom has one electron, and where are they going to go? Into which molecular orbital? Both are going to go down here. So you can write the molecular orbital electron configuration of diatomic hydrogen as sigma 1s 2. Okay, that's how you would write it. So the sigma is a molecular orbital. Now let's soldier on. The number of atomic orbitals that go into the mix equal the number of molecular orbitals that come out. I just had 1s and 1s from the two atoms. How many molecular orbitals did I generate? 2. 2 atomic orbitals in, 2 molecular orbitals out. The atomic orbitals come from each atom involved in the bond. Okay. The second point is the molecular orbitals are filled by the same rules governing the filling of atomic orbitals, right? When we do an alpha diagram, Hund's rule applies, Pauli's exclusion principle. And antibonding orbitals have a larger energetic distance from parent molecular orbitals than bonding orbitals. It just basically means, like we had with hydrogen, we had the 2 hydrogen atoms in the middle. The sigma was downstairs and the sigma star was upstairs, right? And the interesting thing is with sigma type, so this is kind of related to valence bond theory, you've again got sigma pi delta type bonding, depending on the symmetry. And sigma and sigma star, so the bonding between the sigma and the sigma star is always the biggest. Pi and pi star is smaller, delta star is even smaller. Right? So that's the rank order, and that's got to do with the relative strength of sigma versus pi versus delta. Now, the next thing I want to discuss is bond order. Now, bond order is actually, you know, intuitively, we would say, okay, the bond order is 1, which means it's a single bond. The bond order is 2, it's a double bond. That's not really correct. Okay, it's intuitively how we think about bond orders. But formally speaking, the bond order is actually derived from the molecular orbital diagram in a formal sense by looking at the molecular orbital diagram and seeing how many electrons are in the bonding orbital or bonding molecular orbitals. How many electrons are in the anti-bonding molecular orbitals divided by 2. Now, in the case of hydrogen, we just had 2 electrons in the sigma orbital, the sigma 1s orbital. So what's the electron configuration? What's the bond order? 1. Because I have 2 minus 0 over 2. Now that fits with our expectations of hydrogen. We know that there's a single bond, so we expect the bond order to be 1. Makes sense. Now, that's the simple case. Of course, we can make molecular orbitals of the other orbitals, right? Not just S. We can do it with P. We can do it with D, with F. All of that. What's important is to match symmetry with symmetry. But anyway, let's just look now at how we would look at the molecular orbital diagram of this homodiatomic difluorine. Right. Now the question is, what do we have in fluorine? By the way, when we're doing molecular orbital theory, we only consider the outermost valence electrons. We don't consider the core electrons because they're not involved in bonding. So for fluorine in F2, let's look at what's happening here. This is quite a mouthful. But I have in each fluorine atom, let's call it F1 and F2. This is the ground state electron configuration of both fluorine atoms. So it's quite simple. I put the two individual atoms, I write down their electron configurations, right? And then I build the molecular orbital diagram. Now, as we just saw with hydrogen, the S's are going to overlap, right, to form a sigma 2s and a sigma 2 star s. There they are. We just saw that with hydrogen. But the p orbitals, the three p orbitals, can overlap in two different ways. They can overlap in a head-on fashion, a sigma fashion, right, which is going to generate a sigma and a sigma star orbital. The sigma just means it's sigma symmetric, like we have with valence bond theory. And you can have a situation where they overlap in a side-on fashion, okay? So with p orbitals, there are three of them. Remember, they're 90 degrees to each other. Here's the one atom, here's the other. One of those p orbitals is going to form a sigma bond, and the other two are going to form pi bonds, right? So p orbitals can be sigma symmetric. And so what you see here is the pz, because z by convention is the one that we always choose to be sigma symmetric, forms a sigma 2pz, sigma 2, well, we just call it sigma 2pz star, right? Remember what I said a moment ago? Sigma sigma star always has the biggest separation, and then come the pi ones. Now there's two of them. There's two of them, right? These two, well, you know what I mean. There's two p orbitals that are capable of a pi symmetric bond, and they're going to form two degenerate pi molecular orbitals and two degenerate pi star anti-bonding orbitals. And all I have, so those are my molecular orbitals, right? We call it 2p pi, 2py, pi 2px, and pi star, for the star means anti-bonding, 2py, 2px. Now, we call the HOMO the highest energy occupied molecular orbital, which in this case is this guy here. That's an important one. HOMO, highest energy occupied molecular orbital, which are these two, which are degenerate. They're both HOMOs. And the LUMO is called the lowest energy unoccupied molecular orbital, which in this case is the sigma star 2pz. Now, we talk about HOMOs and LUMOs because they're frontier orbitals. And if you want to understand the reactivity of fluorine as a molecule, understanding where the HOMO and the LUMO is located in the molecule, because usually these somehow reside on one side or the other, is very important in predicting reactivity. They're called frontier orbitals. Okay? HOMO and LUMO. An important word. Frontier orbitals. Now, that's the situation for a simple diatomic system. Okay, for a simple diatomic system. Oh, and of course, the other thing we need to do is then take all the electrons we have here. How many is that? 2, 4, 6, 7 to 14 electrons, and put them in here. Notice that's what we end up with. If I were to calculate the bond order, what would it be between the two fluorine atoms? 1. Sum all the sigma orbitals, that's 2, 4, 6, 8, minus the anti-bonding orbitals, 2, 4, 6. 8 minus 6 divided by 2 is 1. And that's consistent with the expectations of fluorine, right? That if there's a single bond between the fluorine atoms. Okay. Now, let's proceed. Now, for some reason, I really want to show you this video, but I had problems this morning. Let's try. I don't think this worked, actually. All right, I'm just going to walk you through. You can watch this video at home. If you take liquid oxygen and you pour it through a magnet, right? Conducting magnet. You'll see that the oxygen actually interacts with the magnetic field, suggesting that oxygen is magnetic in its ground state. Now, if we think about the valence bond picture of oxygen and the Lewis structure of oxygen, is there any indication that it behaves magnetically? Yes or no?
No.
No. Everything is nicely closed. We've got nicely paired electrons everywhere. There's no unpaired electrons. But the experimental fact is that oxygen in its ground state has a so-called triplet ground state. It's got unpaired electrons that interact with the magnetic field. The only way we can explain that is with molecular orbital theory. Please do watch this video. It's a great video. And if we look at the molecular orbital diagram of dioxygen, which is analogous to difluorine, we have, again, sigma, sigma star, sigma 2pz, sigma 2pz star, pi 2px, pi 2py. It's exactly the same as what we just saw, but what do you notice? What do you notice in the HOMO, the highest energy occupied molecular orbital? 2 unpaired electrons. That's the ground state. And you'll see oxygen, if you have liquid oxygen, it's blue in color. It's got this light blue color. It's beautiful. Liquid oxygen is blue. And that's because you have electronic transitions possible, right, of these unpaired electrons. But they're unpaired. And so because they're unpaired in the ground states, oxygen is in fact interacting with a magnetic field. And this is not something that you would be able to explain with valence bond theory that we just saw a moment ago. So this is a very important and correct model, even for something as simple as oxygen. This is what these molecular orbitals actually look like, right? This has been modeled using computational methods. You have a sigma, right? This is what the sigma star orbital looks like. The green and the red indicate different phases of the orbitals. That is what the sigma pz orbital looks like, okay? That's what it looks like. This is what a pi molecular orbital looks like. Notice these are the oxygen atoms. It's delocalized over the whole molecule. And this is what a pi star orbital looks like. Different phases. And this is what the sigma star orbital looks like for a a sigma type atomic orbital. So this is quite straightforward. Now, let's look at other diatomics, okay? And let's look now at heterodiatomic systems. Now, we've looked at CHE2002 and so on. That's quite straightforward. But what about something like CO? Okay, but before we're going to get there later on. But before we get there, I just want us to look at something else quickly. Just a moment. I'm going to come back to this. And what I want to come down to is we have this notion of sp mixing, and this confuses the hell out of you. Now we've just seen for oxygen and fluorine the atomic orbital diagram on the right, or sorry, the molecular orbital diagram on the right. No sp mixing. And the reason why you have no sp mixing, well, that basically means is these orbitals are not interfering with each other. Okay, and the reason why you have that is that if you look at the relative energies in oxygen and fluorine of the s and the p orbitals, they're pretty far apart from each other. That's what we see here. So here's oxygen and here's fluorine. Here's the 2p and here's the 2s. They're far away from each other. Here's the 2p and here's the 2s, even further away from each other. So if I draw a molecular orbital diagram based on the principles I just showed you, the s and the p orbitals are not going to interact with each other, and there's going to be no sp mixing. But if I go from nitrogen to carbon to boron and so on, these S and P orbitals get much closer to each other, okay, much, much closer. And that enables something called SP mixing. Now, all that happens in SP mixing is that the order of the molecular orbital diagram of the molecular orbitals swap around. Sorry. So here I've got the hypothetical B2 molecule. It doesn't exist, but let's pretend it does. B2 diboron. There is SP mixing. So what the effect of that is essentially that what SP mixing does is it lowers the energy of the P of the P molecular orbitals or the pi molecular orbitals and increases the energy of the sigma bonding molecule. So all that happens is the effect that those two swap around, right? And you can see with these dotted lines what's actually happening here. You can actually see that because the S and the P are so close in energy, right, that you have this phenomenon where you have an interaction, watch this, between this S and this sigma and this P and this sigma star down here. So there's all these second order interactions going on. And the take-home message is quite simple, and that is that oxygen and fluorine have no SP mixing. I'm now talking about homodinuclear molecules, O2, Fe2, B2, whatever, P2, homodinuclear, the same atom. Fluorine and oxygen has no SP mixing, but the rest do. The rest do. And the reason for that is, I mean, that's not just something to commit to memory. You can actually see that clearly from this. Okay, so SP mixing in the case of everything except O2 and F2, where there's no SP mixing. And the consequence of SP mixing is that the order of the sigma and the pi of the p orbital swaps around to have these second order interactions. The last thing we need to discuss today, I know we've covered a lot of ground. The last thing I want to discuss in this lecture is, and here you see the overall picture, by the way, of SP mixing. Right? Lithium to C, they all have SP mixing, right? These are the molecular orbitals, sigma, sigma star. But notice what's happening to this guy as he marches. It's sort of the net effect is that it goes down in energy. So here you've got in these for oxygen and fluorine no SP mixing. So the sigma occurs where you would expect it to be actually. But here, because of the second order effects, you have this sigma orbital going up in energy because of this SP mixing. And it's a very nice picture showing you the whole picture for the diatoms. Now, I just want to quickly discuss or end off today's discussion discussing diatomics. And in particular, I want to look at carbon monoxide. Carbon monoxide. Now we've got two heteroatoms. Heteroatoms. Now we can't put, like we just had with oxygen and with fluorine, when we draw the molecular orbital diagram, we have the two atoms and their parent atomic orbitals at exactly the same energies. Now, if I've got two different atoms, the energies of the parent atomic orbitals of the two atoms involved in construction of the molecular orbital diagram or in the molecular orbitals is not going to be the same. Why? Why? Someone.
Atoms, they're not degenerate orbitals.
Yes, well, they get yes, different atoms will have different electronegativity for stars. Again, we just on that diagram, if you experimentally measure the energies of S and P of different elements, they're just different. Okay. So in principle, more electronegative elements have lower energies of their parent orbitals, and that's what we see here. Now, it's actually, in principle, not complicated at all. We're doing exactly what we did before, except now the only thing is we kind of have this aberration in the diagram because we've got carbon and oxygen, and the oxygen is lower in energy. The parent orbitals of oxygen is lower in energy than that of carbon. And you see how that kind of distorts things. But the result is actually the same. So here I've got the molecular orbital diagram of carbon monoxide. This is one of the most important molecular orbital diagrams you will see in your life, because carbon monoxide is one of the most important ligands in coordination in organometallic chemistry. So you have to intuitively and deeply understand the molecular orbital diagram of carbon monoxide as a gas to understand how it's going to react and why and so on. So this is super important. Let's walk through it. So carbon has one s and 3 degenerate p orbitals. That's the ground state electron configuration for carbon, old hat. Oxygen, right? The s is lower in energy, notice. And the p is lower in energy than for carbon, right? Because it's more electronegative. And there they are, ground state electron configuration for oxygen. Now these three lines, by the way, they're degenerate, okay? They have the same energy. So what's going to happen? Well, I've got a sigma. I'm going to form a sigma and a sigma star with these two s's, right? It's a little bit distorted, but they can still overlap. They energetically they don't have the same energy, but they can still overlap. They're close enough to form a sigma-sigma star bonding combination. There we go. Now we're going to have, right, so this line over here is just actually these lines here just indicate p mixing, which occurs more often than it does not. That's the rule of thumb, okay? If you have to bank your money for p-block elements, lighter p-block elements, hetero, and if you really have to guess, there's probably going to be sp mixing, because we just saw for oxygen and fluorine there isn't, but those are exceptions. So you have sp mixing here as well, and we just saw the net result of sp mixing is that you have the sigma orbital going up in energy. And remember, this sigma orbital is actually derived from, in fact, we should correct this. There's a mistake here. And the mistake is, this is the mistake. There should also be a line going like that, right? Because this orbital, this molecular orbital here, right, is, after all, the sigma p orbital. These are the two degenerate pi orbitals, and then you have the corresponding pi and pi star upstairs. Sorry, pi. So sigma. Sorry, this is going to be pi star and sigma star. So let's write them down. So this is going to be sigma 2s. This is sigma star 2s. That's one way of noting them. By the way, I'm using a notation that I'm going to change later on when we discuss molecular symmetry. Then I'm going to start using symbols like gerade and ungerade, G and U, and other weird symbols. But for the purposes of now, considering we haven't done formal group theory, or I haven't introduced you to molecular symmetry labels, let's just stick to this notation. It's perfectly acceptable. This is going to be pi p x and pi p y. This is going to be sigma p z, and these are all bonding. And then I'm going to have right at the top there, that one at the top there, over there is going to be the pi p y and the pi p x star orbitals, and the one right at the top is going to be the sigma p z star, way up there at the ceiling. That is the molecular orbital diagram of a heterodiatomic system. In principle, it's the same as what we saw before. You just have this different starting energies. Now let's talk about homos and lumos. What is the homo in that molecule? Which molecular orbital reflects the homo?
Sigma p z.
Sigma pz. Now, this is the sigma, this thing that's showing here, 3 sigma, that's a sigma pz molecular orbital. What does that tell us? It tells us that that lone pair is sitting where? It's sitting in a sigma type orbital. But what does that tell us? It tells us something about the reactivity of the molecule. It tells us that the lone pair that's sitting in a sigma type orbital is going to attack from that orbital. What is the LUMO in this case? LUMO, what is LUMO? What does that stand for? lowest unoccupied molecular orbital is this here. What's that? Or it's the pi star. The py and the pi py and the pi px star anti-bonding orbitals. Pi star orbitals, they degenerate. This is what the orbitals look like. Notice that's a pi star orbital. The phases are different color. You see that? This is the one that's on the plane of the board. This one's orthogonal to the board. Right? They're the same, but they degenerate. Now, that tells us something else about the molecule. So the frontier orbitals, the LUMO and HOMO, tell us something that's very important in terms of the reactivity of the compound. It tells us that if I take and you can't predict this with the Lewis structure, because the Lewis structure in valence bond theory doesn't tell you anything about the frontier orbitals, right? Which orbitals, because the frontier orbitals in a molecule is going to be where all the chemistry takes place, where there's going to be nucleophilic attacks and electrophilic addition. It's going to take place there. It gives us a locality. We don't get that with valence bond theory. What we get with valence bond theory is it's just like a picture, a static picture. But here we get information about the actual frontier orbitals, and that has major consequences actually for figuring out what the reactivity of the thing is going to be. Now, we've looked today at hetero and homo bimetallic systems. I just want to mention that things can get incredibly complicated very quickly. If you, for example, take something like BF3, this has got 4 atoms. This is what the molecular orbital diagram would look like for that one. Now things get very rapidly complicated. You see I start having A and E. These are symmetry labels. They tell us something about the symmetry, the fundamental symmetry of these orbitals. You have to start looking at group theory. You have to start looking at something called linear combinations of atomic orbitals. It gets very complicated. Okay? We're not going to go there in this course, but this is what, in any event, what the molecular orbital diagram for BF3 looks like, complicated, right? Very complicated. And compare that to the relative simplicity of the Lewis structure and the valence bond picture of BF3. You see the difference? But this reflects reality, and this approaches the reactivity of BF3 much better. You see, it's not actually that complicated. I'm just taking boron, and I'm taking 3 fluorine atoms. I can't take one each at a time. I have to take all 3 of them together and look at all possibilities of the 3 fluorine atoms. It's complicated. But it involves something called a SOLGO, symmetry adapted linear group orbital. Right? It's something we discussed in the 3000 course. We do, don't worry. We're going to come back to this. But for this introductory course, just intuitively understanding diatomics, hetero and homo diatomics is fine. In practice, in a research setting, if you make a molecule, the way to actually get the molecular orbitals is by typically something called density functional theory, DFT, computational methods. This was one of my articles from, I don't know, about 8 years ago, where we made an ion complex, and you can do DFT studies on it. You can actually derive the molecular orbital diagram from these calculations. What you see depicted here are actually the some of the frontier orbitals and what they look like with these balloons. I mean, it looks like balloons, you know, the red and the green, but actually molecular orbitals, showing the locality and delocalization of those molecular orbitals. It's not always necessarily delocalized over everything, but you see there's quite a large degree of delocalization. This is a molecular orbital that corresponds to HOMO -5. It has a specific energy. To derive this by hand would be simply impossible for such a complex molecule. Well, I suppose you could do it for a PhD thesis, but you know, typically one does this by computational methods, and this gives you valuable information about, again, the reactivity. In this case, that ion compound, which by the way was a catalyst, we know that the HOMO is residing here, right? And we know that the LUMO is residing on that phenyl ring in the backbone of that ligand, and that tells us, okay, if the LUMO is there, if I add a nucleophile, it's going to attack the LUMO, right? Do you know what nucleophiles and electrophiles are? Have you all done organic chemistry? Some of you, okay. Well, if I add a reagent, it's going to attack there. So we're getting incredibly important information from molecular orbital theory. And it is the most important theory in chemistry. Questions? Any questions at all? That's a good question. It lowers the energy because if you look at the relative energies, well, what's actually happening is the s orbital, right? The s atomic orbitals and the p atomic orbitals are so close in energy that when they form these molecular orbitals, that the sigma and the pi interact with each other, and effectively the sigma star orbitals actually kind of, if you look at those dotted lines, you can actually see which orbitals are interacting with which. The net effect is that the sigma, actually, not the sigma orbital doesn't really get promoted, the sigma p orbitals. The pi orbitals get stabilized, right? They get stabilized by this sp mixing so that their energy is lower than that of the sigma pz. That's the net effect. And you can see that actually from which orbitals are interacting. Other questions? Anything at all? Right, this video is recorded. I know that we moved very quickly today. Next week, we're going to crystal field theory, and it's going to be a little bit lighter. And so we will certainly have more questions next